Hi, I am Sanjay Patel. In this lecture, we are going to understand the concept of triple integrals and how to compute the triple integrals. We are not going to learn the rigorous definition of triple integral as similarly as we have defined the double integrals in our previous videos. We'll understand how to find the value of triple integrals because the application of these double and triple integrals are very important. So first of all, let me tell you in a simple way that integral of functions of three variables defined on some say volume defined over a volume in three dimension is called triple integral. So let me explain this way. Let f be a function from AB cross CD cross EF. So this is a three-dimensional object, and it is a cuboid to R be a real valued function of three variables x, y, and z. Okay, we'll put this cuboid, or you can say parallelepiped, or as AB cross CD cross EF. Okay, so our function will be like this. Suppose we have some x, y, and z axis like this. Suppose this is x axis, this is y axis, origin, and this is z axis. And I take this type of cuboid. Let me consider this and put this somewhere here. So this is in the space, and this cuboid, okay, this is here, this changes from say A to B, so I can consider something like this. This is A to B. This length is changes from C to D somewhere here, and this height changes from say E to F on the Z axis. E to F. Okay. So this goes to this and this goes to this. Fine. And our function is defined over this volume, and this f is a function from this to set of real numbers. Suppose this is set of real numbers. So f is a function from this volume V to R. So if you take any point here in this cuboid, say any point x, y, z, then its value under this function is somewhere here, say f of x, y, z. So f is a function of three variables. For example, you can take if f you take like this, f from say, let me take a cube here, f from 0, 1 cross 0, 1 cross 0, 1 to R as f of x, y, z is equal to x plus y plus z. So this is an example of function of three variables, and if you take any x, y, z in each of these intervals, x equal to 1 by 2, y is equal to 1 by 2, and z is equal to 1 by 2, then its value you can obtain just by plugging these numbers, and you get 3 by 2. So it is always a real number. F is a function of these three variables, and its value is always real, defined on this volume. And for such a function, the integral we define, then the domain of that region of integration is this volume, and it is denoted by the following sign. So let me define this way. We define the triple integral of the function f of x comma y comma z over the volume V over the volume V as triple integral. So there are three integral signs over the volume V of the function f x comma y comma z dv, or you can say dx into dy into dz. Okay, this is defined as according to our convention. We are going to just understand how to compute this. So I am going to define this integral, assuming that this integral exists. This is defined as integral a to b, integral c to d, integral e to f, f of x comma y comma z, dx, dy, dz. And the meaning of this triple integral, here you understand in this form, that this is to be integrated with respect to, say, the z first, then with respect to y, and then with respect to x. And all the limits of integration here are constants. So more precisely, you can understand like this. This x is equal to a to b, then this into y is equal to c to d. Let me and z is equal to e to f, f of x comma y comma z. Do not confuse between this f and this f, or I can take some, say, other notation, but we don't want to change everything, so let me just keep it as it is. So f e to f, then first with respect to z. So this function, when you integrate with respect to z, x and y are kept as constant, and we integrate as a simple function of one variable z, and then we put the limits of integration, z is equal to f and z is equal to e. So we get some expression into as a function of two variables x and y, and then it is to be integrated with respect to y, okay, as usual, and finally with respect to x. Okay, so this way you can compute the triple integral over the given volume. Just to understand this, let us take one simple example. Remember, we are not learning the rigorous definition or concept of triple integral. It requires a lot of other things. Our main focus is how to compute triple integrals. So first, let me take one simple, very simple example of this type. So find the value of the triple integral over a volume V of this function x into y dx dy dz, where the volume V is the cross product of 0, 1, then say, let me take 1 comma 2, and let us take minus 1 comma 1. Okay, so it is set of all x, y, z, where x belongs to this, y belongs to this, and z belongs to this. More precisely, we can write this way also. The volume is actually the set of all x, y, z in R3 belongs to R3 such that x belongs to closed interval 0, 1. So 0 less than or equal to x less than or equal to 1. Y is between 1 and 2 and z is between -1 and 1. Okay. We want to find the volume integral of this function. So our function here in this case is f of x comma y comma z is equal to x into y for all x, y, z belongs to the volume V. So this triple integral over the volume V, x into y dx dy dz, according to our definition, is integral 0 to 1, integral 1 to 2, and integral -1 to +1 x into y dx dy dz. Okay. So this I can compute in this order as I have explained, first with respect to z, then with respect to y, and then with respect to x. So this is equal to integral 0 to 1, integral 1 to 2, and then I can write integral -1 to 1. X into y is constant, I can keep it outside, and 1 dz, then dy, and then say dx. Let me write this way. dy and let me write dx dy. Okay. So this is equal to 0 to 1, 1 to 2, xy, and the integral of 1 is z, -1 to 1. These are the limits of z, remember, into dx dy. So it's a very simple integral, just to understand how one can evaluate this type of triple integrals. So 0 to 1, 1 to 2, and you know the value of this integral is say 1 minus -1, so it is 2 dx dy. So now this becomes our simple double integral of functions of two variables, x into y dx dy. So integrate this with respect to y first and then with respect to x. Okay, so this is equal to 2 times integral 0 to 1, these are the limits of x, remember, into integral 1 to 2, these are the limits of y, x into y dy, and then dx. So this is equal to 2 into integral 0 to 1. Here x is constant, so we integrate y with respect to y. So the value of this is x into y square by 2, and that we have to compute for y equal to 1 to 2, and then integrate with respect to x. Okay. So putting the values of the variable in this integration, where x is not affected, yes, x remains as it is. So I can keep x outside also and write, put the value of y equal to 2 first. So 2 square upon 2 minus y is equal to 1. So 1 upon 2. And then this is to be integrated with respect to x. So 2 into integral 0 to 1. This is 4 upon 2, that is 2. 2 minus 1 by 2 is say 3 by 2. So x into 3 by 2 dx. So this gives us 3 times integral 0 to 1 x dx. These two will be cancelled. So this is equal to 3 times integral of x is, x square by 2, 0 to 1. And putting finally the values of the limits of x, putting x equal to 1 first, so 1 by 2 minus 0. So final answer is 3 by 2. So volume integral of the given function x into y over this cuboid, or you can say parallelepiped, is this 3 by 2. Remember, here all the constants, all the limits of integration are constants. And when all the limits of integration are constants, you can, and the function is integrable or it is continuous, you can change the order and integrate in any order. I mean, you can integrate with respect to y first, then with respect to z, then with respect to x, and so on. There are many possibilities. So you can use any of that, say, order of integration, but provided the function is integrable, or say you can say more strictly that function is continuous and it must be integrable, and you can do that change of order in any manner. Okay, but remember, in general, our volume, what we are discussing here, in general, if f is a function, let me write this as a, say, something like this, triple integral over any solid, in R3. That solid region, okay, let me write this, triple integral over any region of any shape, any region in R3. Okay, so let V be any region in R3, okay, be a region, or you can say a volume or a solid region, which is bounded by, say, x equal to a, x is equal to b, y is equal to phi of x, y is equal to psi of x, and now the new thing is, say, z is equal to, let me call this as phi 1, phi 2, so that, say, phi 1 of x comma y, and z is equal to psi 1 of x comma y. So our volume is bounded, or the solid region in R3 is bounded by these curves and this kind of surfaces. You know, this kind of equation in R2 represents a curve, and this type of equations are nothing but the equation of surfaces. Okay, any function of two variables, if you draw the graph, you will get some surface. So z is equal to phi of xy and z is equal to psi of xy are surfaces. So region is bounded by these surfaces, these lines and curves and so on. Then I can write down, then we define the triple integral of the function f of x comma y comma z, okay, dx dy dz over the volume V as the repeated integral given by x is equal to a to b. Then I can say y is equal to phi of x to psi of x, and finally z is equal to phi 1 of x comma y to z is equal to psi 1 of x comma y, f of x comma y comma z into dz into dy and then dx. So this is a repeated integral which can be expressed in the form this can be written as triple integral a to b, then phi of x to psi of x, then phi 1 of x comma y to psi 1 of x comma y, f of x, y, z, dx, dy, and dz. Remember, we have to integrate again in this order from right to left. So first with respect to z, then with respect to y, and then with respect to x finally. So if the triple integral of a function f of x comma y comma z over volume V exists, which is bounded by these curves and surfaces, then we can express in this form of repeated integral. Remember, here f is a function from V to R. F is a function from V to R of three variables. There are many other repeated integral possible. If the function is continuous, then you can integrate this in any order, because every continuous function is always integrable. Whether it is double integral or when you talk about triple integral, all continuous functions are nice functions. They are always integrable functions. Okay. So another important thing I want to tell you is whenever you are evaluating these integrals in practice, if you are integrating with respect to z first, remember the limits of z are given here. These are the limits of z, and they are always functions of the remaining two variables x and y. Okay, once this is done, the next limits are functions of the remaining variable, that is x. So what I want to say is we can have many different types of repeated integrals. For example, let me explain. We can also have triple integral over the volume V of the function f dx, dy, dz is equal to integral, say, c to d, say y is equal to c to d, and the z is equal to phi of y to psi of y, and finally x is equal to phi 1 of x is equal to phi 1 of function of x and z, and x is equal to psi 1 of x comma z, f of x, y, z. Now the order will be like this. It is, say, dy, dz, and dx. So it is first integrated with respect to this x, and when you integrate with respect to x first, remember the limits of x is either constants or they are functions of the remaining variable. Again, I made a mistake here, sorry. This is not x. X is the function of y and z. X is the function of y and z. So whenever you integrate first with respect to x, the limits of x will be either constant or functions of the remaining variables, that is y and z. Okay. Once this integral is done, the second integral, the variable is z. So when you integrate with respect to z, x is gone. So limits of z will be either constants or function of the remaining variable, that is y. So here I written z is the function of y. And then finally, nothing remains, only variable x is left, variable y is left. Finally, the limits of y are always constants. So there are many possibilities. You can shuffle this order and compute the triple integral. Let us take one simple example. Okay, so let me write examples. So I'm taking the first one. Evaluate the integral x is equal to 0 to 1, y is equal to 1 to, say, x square, and z is equal to 2y to x plus y of the function x, and it is dx, dy, dz. Okay, just for the practice, we are finding the value of this integral. So the given integral is equal to, means this integral, I'm not writing it again, first with respect to z, then with respect to y, and then with respect to, say, x. So as I told you, when you integrate with respect to z first, the limits of z will be either constants or functions of x and y. So here you can see they are functions of x and y. And once it is done with respect to z, the next variable we are integrating here is with respect to y. So limits of y will be function of the remaining variable, which is x, or it is constant. So here you see y limit is 1, and here y limit, upper limit is x square, it is a function of x. And finally, whatever is left, that is the third variable x, its limit will be always constants. So let us find the value of this integral. It is integrated with respect to, say, z first, y is equal to 1 to x square, and then let me write z is equal to 2y to x plus y, x dz dy, and then dx. Okay, so this is equal to integral 0 to 1. We know the last limit is limit of x. Okay, no need to write that. And here y is equal to 1 to x square. X is constant, so integral of x with respect to z is x into, say, z, because this you can treat as x into 1, and integral of 1 with respect to z is z. And we have to substitute the limits of z is equal to 2y and z is equal to x plus y. And this is to be integrated with respect to y and then with respect to x. So this is equal to integral 0 to 1, then integral y is equal to 1 to x square. Now these are the limits of z, remember. So wherever z appears in this integral, we have to substitute the value of upper limit and lower limit. The upper limit is x plus y. So what I will be doing here is x into x plus y, just putting in place of z only, because these are the values of z, minus x, and put z is equal to 2 into y, so 2y, and then dy into dx. Simplify this and then integrate with respect to y. So this is equal to integral 0 to 1, and then integral say y is equal to 1 to x square. This you can simplify, is x square plus xy minus 2xy. It will give you x square minus xy dy dx. This is x into y, and this is minus 2 into x into y. So this is equal to integral 0 to 1, and then integrating now this function with respect to y. X is constant, so integral of x square is integral of x square into 1, which is x square into y, minus integral of x into y. So x is constant as it is, and integral of y is y square by 2. And then we substitute the limits of integration for y, which is y is equal to 1 and y is equal to x square. And finally, whatever answer we get, it is to be integrated in the end with respect to x. So the next, this is equal to integral 0 to 1. We substitute the limits of integration now. First we put y is equal to x square. Remember, these are the limits of y. First we put the upper limit everywhere in this, wherever y appears. So what I will get is x square as it is, and y is equal to x square. Okay, minus x as it is, y is equal to x square. So x square square by 2. This is the first part, minus, you know that fundamental theorem, f of b minus f of a. Now we put the lower limit wherever y appears. So x square into 1 minus x into 1 square by 2, and then this is to be integrated with respect to x. So it is very interesting and very simple. So let us simplify this. This is x raised to 4. This is x raised to 4 minus x. So it is x raised to 5 by 2. Then this is minus x square and minus plus x by 2. Is this fine? Yes. Okay. So this is nothing but simple integral of function of one variable, which I can write directly. Integral of x raised to 4 is x raised to 5 by 5 minus integral of x raised to 5 by 2 is x raised to 6 by 6 into 2, so it is 12. This is x cubed by 3, and integral of x by 2 is x cubed by 3 into 2, that is 6. And then we put the limits of integration 0 to 1. Okay. So just plugging the values, upper limit is 1. So we'll get 1 by 5 minus 1 by 12. This minus 0, because everywhere x is there. When you put x equals 0, all this becomes 0. So what is left is only this much. Okay. So here let us simplify this. So it is very simple. Just LCM we take here is, so that is 60, it's clear. And putting all the values, we get 12, 12 5 is 60, 23 is 60, and 10, plus 10 there. Okay, so minus 20 plus 10 is minus 10, minus 5 is minus 15, and minus 3. So it is minus 3 by 60. So it is minus 1 upon 20. Okay, so this way you can compute the triple integral in terms of repeated integrals. Let us see how to compute the triple integral over any say irregular solid or solid object in 3 dimension. So let us start with the next problem. So the second example is evaluate the triple integral of x square dx dy dz over the volume V, where V is the volume between the three coordinate planes, that is x, y, y, z, and zx planes, and the plane, there is one more, that is given by x plus y plus z is equal to a, where a is some positive number, say, just for simplicity. So this type of problems are important. So you want to understand how to evaluate this triple integral over the given region in 3 dimensions. So first I will draw the figure for this. So let me choose the different axes in 3D. So this is okay. So let us take one. Okay. Oh, sorry. Let us take this as says this is z-axis. Okay, then I am taking somewhere. So this is my y-axis. Okay. Okay. Let me take the y-axis like this, okay, and the z-axis, or rather in the y-x-axis, say something like this. Okay, so this is x-axis, this is my y-axis, this is z-axis, and this is our origin. Okay, to have a three-dimensional, say, figure or the solid to understand, I'm taking the x, y, z axis in this orientation. Now let me put the plane x plus y plus z is equal to a. You know what is the equation x plus y plus z is equal to a? The region of integration is bounded between the three coordinate planes, that is x, y, y, z, zx, that is clear, and the plane x plus y plus z is equal to a. You know x plus y plus z is equal to a is a plane making intercept a on all the three coordinate axes. So I can put a triangle. Okay, this is not coming properly. So I can draw a triangle type of region. Okay. Yes. And say this. Fine. So this is a plane. You can call this as say A, B, and C. The vertices of this triangle where this plane meets the three axes A, B, and C. And this is the x-intercept, which is A. So coordinates of this point are A, 0, 0. Coordinates of this point are 0, A, 0. And this is 0, 0, C. So equation of this plane is x plus y plus z is equal to A. Just recall, you have done in your higher secondary course, the equation of a plane making intercept A, B, C is x upon A plus y upon B plus z upon C is equal to 1. That means this plane is intersecting the three axes x, y, and z axis respectively at A, 0, 0, 0, B, 0, and 0, 0, C. Here all the three intercepts are equal. This, and this all are equal. Okay. And this is a straight line joining this two points A, 0, and 0, A. So I can also write down the equation of this straight line as this straight line is given by, it is x upon A plus y upon A is equal to 1. So I can write x plus y is equal to A. Like equation of plane, equation of a line making intercept A and B on x and y axis is x upon A plus y upon B is equal to 1. So I'm using that fact and writing the equation directly. X upon A plus y upon A is equal to 1. So that gives us x plus y is equal to A. It's clear? So this is the, say, three-dimensional volume in which this is there are how many sides? One. This is the triangular plane, that is one side, and the three other sides are these coordinate planes. This xy plane here, this is the xy plane, and this is yz plane, and this plane OAZ you can say as, say, your xz plane. We want to integrate in this region. So how to write the limits of integration, that is very important. So let me write the triple integral of the function x square dx dy dz over the given volume is equal to, we want to write in terms of some iterated integral. Let us decide that we want to integrate with respect to z first. If you want to integrate with respect to z, then you always take a strip parallel to z-axis in the region of integration. So I take a strip parallel to z-axis, arbitrary strip parallel to z-axis in the region of integration. So if you take a strip like this, yes, something like this. And if you move this strip, you can say for all the position of this strip, if it is here, the lower end and the upper end of the strip are remaining on the same surface. Now we have to think of surface, not curve, because when you integrate with respect to z first, remember z is the first variable you are integrating. So the limits of z will be functions of x and y. In fact, limits of z are surfaces. So we have to find out the equation of the lower surface and the upper surface, that is the end points of this strip. So even if you take a strip here, the lower end is on this xy plane. This is the xy plane. This shaded region is xy plane, okay, whose equation you know is z equal to 0. So equation of this region, that is this region is xy plane, is z equal to 0. So the lower end of this strip is the surface given by z is equal to 0, which you can say it is phi of x comma y, function of x and y. And the upper end of the strip is on this plane, whose equation is given by this, which I can write as z is equal to a minus x minus y as a function of x and y. So z is equal to psi of x comma y. So this end you can write as z is equal to a minus x minus y. So z varies from z equal to 0 to z is equal to a minus x minus y. Then to determine the limits of next variable, that is y, we take again, as in the similar way of double integral, we take a strip parallel to the y-axis. So if we take a strip parallel to y-axis, say something like this, any strip parallel to y-axis, this is the y-axis. So if I take a strip parallel to y-axis, it goes like this. Then for all the position of this strip, the left end curve is on this x-axis, where the equation of y, the curve y is equal to 0, which is the equation of the x-axis, okay, and this curve, which is the straight line AB, whose equation is x plus y equal to a, which I can write as y is equal to a minus x. So this y is a function of, say, x only. So y is equal to phi 1x, y is equal to phi 1 of x to y is equal to psi 1 of x. Phi 1 of x to y is equal to psi 1 of x. So I can write down this integral as first the limits of z as a function of x and y, the surfaces which we have discussed. Z varies from 0 to a minus x minus y, and then limits of y, that is y is equal to from this 0 to y is equal to a minus x, which are functions of x only, and finally limits of x, which are constants. That we have to identify by moving in this solid what is the minimum value of x and what is the maximum value of x in this whole region. The minimum value of x is 0, which is obtained at this place. Minimum value of x is 0, whose coordinates are 0, 0, 0. And the maximum value of x, when you exit the region, this region from anywhere, the maximum value of x is this value a. So x varies from 0 to a. And then we can integrate the given function, which is x square, and then into, say, dx, dy, dz. So first with respect to z, then with respect to y, and then with respect to x. So it remains to find the value of this integral only. So let us compute this integral. So this is equal to integral x equal to 0 to a, and then y is equal to 0 to a minus x. X square is constant, I can keep outside. and integral of 1 is, well, let me write one more step. This integral z is equal to 0 to a minus x minus y 1 dz and then dy and then dx. So write like this. Okay, so this is equal to integral 0 to a, x equal to 0 to a, and then integral y is equal to 0 to a minus x square, and then I can write, okay, this integral of z is, integral of 1 is z, and limits of integration is z is equal to 0 to a minus x minus y into dy and then dx. Okay, so this is equal to integral 0 to a, integral y is equal to 0 to a minus x square into the value of this by putting z is equal to a minus x minus y, and then z is equal to 0, okay, into dy and then dx. So this is equal to integral 0 to a. I can multiply this with say x square and write as x square into a. So a minus a into x square minus x cube minus x square into y. This is 0, so it will go dy and then with respect to dx. So it is a matter of now simple double integral. So 0 to a. This I can integrate with respect to y by keeping x constant. So integral of a into x square is a into x square into y. Integral of x cube is x cube into y. Integral of x square into y. So x square is constant. So minus x square into integral of y is y square by 2. And this is to be evaluated from y equal to 0 to y is equal to a minus x. Remember, these are the limits of y only. So wherever y appears in this integral, we have to substitute the value of y. So this gives us integral 0 to a, okay, into, first I substitute y equal to a minus x everywhere. So ax square into a minus x cube into a minus x, then minus x square by 2 into a minus x whole square, and then y equal to 0. The second term is 0, 0, 0, because everywhere y appears and we have to put y equal to 0. So everything goes and it is simply 0. So further simplifying, this is 0 to a, and let us expand this. So what we can do here is simplifying. We'll get a square into x square minus a into x cube, then minus ax cube again, minus plus x raised to 4 here, and then here it is perfect square. So it is a square minus 2ax plus x square. Multiplying by a square, we'll get minus a square by 2 into x square. Then the middle term is minus 2ax, which is multiplied with this. So minus becomes plus, 2 gets cancelled. It is 2ax, so 2 cancels, and a into x square gives us a into x cube. And finally, last term is x square plus x square into this is minus x raised to 4 by 2. And this is to be integrated with respect to x. Okay. Note that these two will be cancelled. This ax cube and this ax cube will be cancelled. Is there anything else? A square by x, a square, x square by 2. Yes, I can simplify further and write it as this and this. This is a square x square. This is 1 by 2 times x square x square. So further simplifying, writing this as integral 0 to a into, first I'm writing a square x square minus this. So this 1 by 2 times a square x square, then minus ax cube. Okay. Then x raised to 4 and minus x raised to 4 by 2 again becomes 1 by 2 times x raised to 4. Something like t minus 1 by 2 times t, that is 1 by 2 t. And integrating now, it's simple. So 1 by 2 a square into x cube by 3 minus a into x raised to 4 by 4 plus 1 by 2 into x raised to 5 by 5 and then 0 to a. Just putting the values of these limits of integration, which are the limits of x only. First we put x equal to a. So what will you get is, putting x equal to a, this is a cube, this is a square. So a raised to 5 by 6 minus, putting x equal to a raised to 5 by 4 plus a raised to 5 by 10 and minus everywhere x is there. So putting x equal to 0, all terms are 0. So we are getting this as our final answer. And let us simplify further. So this is 6, 4 3s are 12, 12 5s are 60. So what will be the LCM here? It is 60, yes? And a raised to 5 is common, so I can write it outside. What remains is, here it is 10 minus 60 means 15 4s are 60 plus 10 6 are 60. Okay, fine. So 16 minus, 10 plus 6 is 16 minus 15 is 1. So it is finally a raised to 5 by 60. So this is our final answer. Okay. Let me give you one more problem for practice, and it is exactly same region. I'm just with simple change of numbers. So you can do this on your own, and we come to end of this lecture. See, the problem of evaluating this triple integral, the function is changed and the volume is exactly the same, enclosed between the three coordinate planes and the plane given by x plus y plus z is equal to 1. That was x plus y plus z is equal to a. So just in that figure also you can change a equal to 1 and compute this triple integral. Okay, we'll do some more practice and also see how to change variables in double and triple integrals in our next lectures, which are very, very important topics. So till then, goodbye. Thank you.